Hello everyone, welcome to today's presentation. My name is Savannah Hinchin and I am with EOS Remediation. Today's topic is Bioremediation 101, the intro. And today we have Dr. Robert Borden, who is a principal engineer at Solutions-IES, presenting for us. So a couple announcements before we pass the torch. Ed Alpern was out in Japan over, I guess, the last week in October with the U.S. Department of Commerce and CGC. The U.S. Department of Commerce recognized CGC as a valuable export partner with EOS Remediation. So in that picture you can see Ed with the president of CGC and Mr. Jason Evans, who is the second secretary with the U.S. Embassy. And then a couple reminders is we still have the EOS design tool available through our website. Please access it and let us know how it's working, how you like it. And we've also been making enhancements, and there's new information on our EOS technical library on our website. For the winter, we're in a bit of a conference hiatus until March, when we will be at REMTech in Colorado. So I will let you guys listen to Dr. Borden now, and we'll take questions at the end.
All right, thank you, Savannah. Hi, I'm Bob Borden. As Savannah said, I'm a principal engineer with Solutions-IES. I just retired about a year ago from North Carolina State University, so now I'm officially Professor Emeritus, and I'm going to be giving today's webinar. So first of all, once again, remind everybody, this is supposed to be a very sort of basic introduction. If you haven't had much familiarity with anaerobic bioremediation before, we're going to be going over just sort of a very basic background to get you up to speed. And EOS Remediation has actually a series of additional webinars on more advanced topics, so tune in for them if you're interested. Okay, what is anaerobic bioremediation? Basically, the gist of it is you go out to a site, typically we'll inject an organic substrate. That substrate will stimulate microbial growth. It'll ferment to hydrogen and acetate, and then that hydrogen and acetate is used to reduce the target contaminants, as well as consume any background electron acceptors that would sort of compete with that process. Why bioremediation? Well, this slide here, most of this information is taken from an article by folks at GSI. They did I think it was a CERTA-funded project almost a decade ago, where they looked at different costs of different remedial technologies. And bottom line, anaerobic bioremediation was typically, or at least the median cost was less expensive than a lot of the other technologies. I think one of the other advantages of anaerobic bio is that it's fairly easily scalable. A lot of the other technologies like thermal, on a cubic yard basis, they're not super expensive once you get up to a certain volume, but it's really relatively difficult to do a small project with in situ thermal, where it's very easy to do a small bio project. How does it work? Again, this is from the same study, a slightly different paper by Travis McGuire. He looked at treatment performance, and what you see is really all the major technologies generated pretty high removal efficiencies, at least immediately after implementation of the technology, say that first year. I think one of the strengths of anaerobic bio that's really made it more popular is illustrated in this slide here. What the people at GSI did is they plotted measured concentration in a monitoring well right before implementation of the remediation system to measured concentration at different times after. And so that's that C divided by C initial you see on the y-axis, and then the x-axis is time relative to initial implementation. Before implementation, all the lines sort of bounce around a value of 1, or e to the 0 is just 1. And so what that says is, before treatment, there's really no effect. After treatment with chemical oxidation, you see a pretty dramatic decline immediately after, but then you also see that some of that decline goes away and almost looks like the concentrations are rebounding. Maybe not back up to the initial level, but there's certainly you're not getting quite as good a removal 2-3 years out. And I think the common assumption about that is back diffusion from clays or DNAPLs, or there's just some material that didn't get treated. By contrast, if you look at enhanced bioremediation, what you see is initially there's some decent removal, but actually it almost seems like removal is improving over time, or at least for a decent percentages of the treatment systems, where you might start out at just a factor of 10 removal, but then after a few years you're getting 2, 3, 4, even 4 log unit reductions. Again, this is a study that Travis McGuire, the people at GSI, have just recently completed, where what they did is they tried to basically extend that database. The guys at GSI like to use this term ohms, or order of magnitude reductions. So what they do is they go out to, they compile data, I think about almost 40 sites. And what they did is they took the average concentration, actually the geometric mean of the site before implementation of the remediation system. And then they look at the average concentration 1 year after, and then the average concentration at the end of the monitoring period. And so, for example, that first one there, they're showing a 1 log unit or 1 order of magnitude reduction over the first year, and then over the life of the project, a 2 order of magnitude reduction. Now, this is just a hypothetical site, but it sort of illustrates how they do their calculation. Okay, so this is some of the results. I think this is, and again, thanks Travis for sharing this slide with me. But what you see here is the first bar is the reduction that occurred in the first year after treatment, and then the second bar, or the darker color, is the last year of treatment. And you can see there on the left-hand side, the blue colors, what it looks like about maybe 14 of the sites actually improvement increased over time. So you're getting better and better treatment. In the middle, I don't know, what's that look like, 5 or 6 or 7 sites, removal efficiencies were stable. Now, one word of sort of caution about those results, I've actually gone back and looked at a number of them. There was no change in concentration over the remedial period, basically because concentrations were non-detect in the first year, and then they stayed non-detect for the remainder of the project, so you can't get better. But they certainly thought that 65% sustained treatment was very, very promising. Now, there were 35% of the sites where there was at least some evidence of rebound. I think if you look at the first few orange bars, like that first one, the first year after treatment, it was 3 order of magnitude reduction, versus at the end of the project, it was only 2. Well, that's still pretty good. But I think this really sort of illustrates that a lot of these sites, one of the advantages of anaerobic bio is that you do get this longevity, that at least compared to some other technologies, you don't get the rebound, and so it tends to be a long-term protective thing. Obviously, not every site. There are some sites where they rebound, and people had to go back and do more. What are some of the potential contaminants you can treat? I'm sure you're all aware, chlorinated solvents like Ethenes, ethanes, methanes, nitrate, perchlorate, explosives like TNT and RDX. Those materials are actually being biodegraded. There is also the potential to immobilize certain contaminants like chromate or radionuclides like technetium or uranium. You're not actually degrading those, but you're converting them to a less soluble form. They stick to the sediment and they're not mobile anymore. And then finally, anaerobic acid bind drainage can be treated. Okay, just showing you sort of the classic pathway for reductive dechlorination. If you were trying to degrade PCE, what you would do is you'd essentially try to use a microorganism that would add 1 hydrogen to PCE to form TCE and a molecule of hydrochloric acid. Another molecule of hydrogen would convert it to DCE, and then vinyl chloride and ethene. What we know is that the first two steps in that process, PCE to TCE to DCE, there's actually a large number of different organisms that can carry out that step, and they tend to be physically a little bit more robust and widespread. So it's relatively easy to get that initial transformation. Transformation of DCE to vinyl chloride to ethene, at least our current understanding is there's only one known organism, the Helicoides, that can do that transformation. And so what you're going to hear a little bit later on is discussion about why it might be appropriate to actually add that organism, the Helicoides, to a site to accelerate degradation. Okay, electron donor alternatives. There's a lot of different alternatives down there. You could use soluble substrates like fatty acids or sugars like molasses, fructose, whey extract. And these are dissolved. You inject them. The good thing about them is they're very easily degradable, so they generate anaerobic conditions. But sort of maybe one of the downsides is they don't last very long, so you tend to have to re-inject fairly often. You can use solid substrates like mulch or compost, chitin, zero-valent iron, and I know zero-valent iron is an organic substrate, but it does react in the subsurface, releasing hydrogen, so in a way it's really doing a lot of the same things. Or something like EHC, which is essentially a mixture of mulch and ZVI. Advantages of these materials are they're relatively long-lasting. The disadvantage is that, well, they're solid materials, so it tends to be more complicated getting them into the subsurface. You can dig a trench, you can do certain injection things, but again, getting good distribution tends to be a lot harder. Other alternatives, viscous fluid substrates like HRC or even neat vegetable oil some people inject. They work, they're relatively long-lasting. I think the challenge is with these viscous materials is how do you get good distribution? And I'm going to be talking about that a little bit in this talk and a lot more in maybe a future webinar. Or you can do something like an emulsified vegetable oil. For one, this is truth in advertising. This webinar is put out by EOS Remediation, so we're going to be talking about EOS products. I think probably the most common one they use is EOS Pro. It's an emulsified vegetable oil. It includes a soluble substrate, yeast extract, vitamin B12. The emulsified vegetable oil is a slow-release substrate, and it's been used at, I don't know, thousands of sites. It transports well. It's got all sorts of good qualities that Brad and Savannah will be more than happy to tell you about. Okay, how do you look at these different substrates? Well, what we're trying to do in that early slide is we wanted to add hydrogen to PCE to make ethene. Okay, so where does that hydrogen come from? If you add lactic acid to the subsurface, it will ferment, releasing carbon dioxide and hydrogen. If you add carbohydrates like sugars, they ferment the carbon dioxide and hydrogen. Vegetable oil, same thing. Zero-valent iron, not exactly the same thing, but again, it's releasing a hydrogen. So in a way, you can actually compare all these. If you look at soybean oil, it releases many, many more hydrogens per mole, but that's not completely fair because, well, the molecular weight's a whole lot higher. So really a more appropriate way to do it is probably look at hydrogen release per gram of material. And you can see there's, a fairly broad range, like lactate glucose, maybe 0.07 moles per gram versus soybean oil is 0.18. So quite a bit more material. Well, the reason for that is soybean oil is a more reduced material, so it generates more reducing equivalents. I'm sure some people, a lot of places they use ethanol in gasoline. Well, ethanol doesn't provide as many BTUs per gallon as regular petroleum because it's not as reduced. Same way with soybean oil, it provides more reducing equivalents. So how did this all work? This is, two confessions. I've been using this slide for probably more than a decade, but it's a good slide. I think probably in like 1990, we got some soil from the site. We added soybean oil to it. Soil and groundwater from the site, added some soybean oil to it. As you can see there, cis DCE and TCE went down. We got initial accumulation of vinyl chloride in about 40 days, and then eventually the vinyl chloride went down and made a bunch of ethene. And that's pretty standard. You will often see a temporary accumulation of vinyl chloride, but then, at least in a properly managed site, the vinyl chloride will go down and you'll make ethene. So this was the initial incubation. Actually, one of my best grad students, he graduated. We sort of put the bottles on the shelf and ignored it. And then a couple years later, we're like, I wonder what's happening. So we actually went back and looked at those bottles. We respiked with more PCE. And actually, what the graph I'm showing you here is the 5th respike. We added more PCE. And you can see the PCE goes down. That's that red line. We made a little bit of vinyl TCE, a little bit of DCE, a little bit of vinyl chloride, but then eventually made a whole bunch of ethene. Those bottles had not, that's 835 days, that's like 2.5 years, something like that, since the soybean was originally added. So what this really shows is that certain substrates can last a long time in the subsurface. They can do, long-term support. The other thing I want to point out about this is we actually added about 100 micromolar of PCE to these bottles. The first point there was, you see the PCE concentration is like 13 micromolar. We added 100 micromolar PCE, but there's only 13 there. Well, essentially, that first point is actually, I think, the day after we added it. What happened is the PCE absorbed to the soybean oil. It's not in the aqueous phase, so we can't measure it. But then over about that, maybe a month, 2-month period, the PCE degraded, but then it desorbed from the oil and more degraded. It degraded, more desorbed, and eventually we got essentially 100% of the PCE back as ethene. So, some people worry about, does this, if you're adding this vegetable oil, will the contaminants sorb to it? Well, they do sorb initially, but they do come back out and they do eventually degrade. So that's not, if you're worried about over 30 days, maybe, but, over a long period of time, it's really not an issue. Now, one of the things that we started using when I first started doing this, we used really principally just emulsified vegetable oil. But over time, we've modified the products to include other things. One of the things that I feel real important is that, at least in all the projects that I do, I typically use a product with yeast extract and B12. Why? Well, here's some microcosms from Paul Hatzinger. He wasn't, the company was Shaw at the time, but it's now CB&I Federal. They did incubations looking at degradation of perchlorate, that's ClO4, and RDX, an explosive, over time. And you can see with the different substrates there were, at the top graph, a number of the substrates really didn't do much of anything. Versus the EOS product, it was at the time was called EOS 598, but now it's called EOS Pro. That includes both the fat, the carbohydrate, the proteins, and the vitamins. And you can clearly see, we got more rapid, or Paul got more rapid degradation with that product. It was real surprising because EOS, like if you compare lactate by itself, really didn't do much. Soybean oil, crude soybean oil by itself didn't do much. But apparently that combination of materials worked much better. Why? I can't say really why I know precisely. But to me, my take-home message is, well, just like you. I mean, you might be able to live on pure fat, but certainly a balanced diet that includes some fat, some protein, some carbohydrates, maybe a vitamin pill. You're going to grow better. You're going to have be healthier, and you're going to get better results. It's not that different for people as it is for bacteria. Okay, how much do you need? Well, there's really 2 ways to look at this. The first way is just looking at how much substrate is required for biodegradation. This were results from some early projects we did. We actually injected EOS in a biobarrier configuration. We monitored upgrading the barrier and downgrading the barrier, and we could actually calculate how much EOS was being consumed by the different electron acceptors. What you see is the amount of EOS being consumed for oxygen and iron and the chlorinated VOCs was really absolutely trivial. Methane is significant, but it certainly was not the major component. The biggest thing is just dissolved organic carbon, TOC, being released down gradient. That's not necessarily a bad thing, but it is going to deplete your barrier over time. And then the other item is sulfate. At one of the sites, the sulfate concentration was relatively low, so it was not important. But another site, we had really high sulfate concentration. So that was by far the large majority of the electron donor demand. So bottom line conclusion, the amount of carbon you need, well, it's going to depend on the groundwater velocity and the different electron acceptors that are flowing into the treatment area. If you have a high velocity with a lot of background electron acceptors, you're going to burn up the carbon quicker. And that's just life. That's one component. The second component really has to do with distribution. Now, I'm really focusing here on two different types of materials, soluble substrates or emulsified oil. In both cases, I'm a real strong believer in, well, I'm absolutely sure of this, to get good treatment, you need to bring the electron donor, the organic substrate, into close contact with the contaminant. If the contaminant's over here, at one location and the substrate's 2 or 3 feet away, it doesn't do any good. They have to meet each other. To get good treatment, you have to inject the substrate and then you have to spread it out. With soluble substrates, one advantage is that you can inject it and they actually can drift with ambient groundwater flow. Or at least that's, in theory, a real advantage. In practice, I think what people see is that typically a soluble substrate like molasses or lactate might have a half-life of like 10 days. So after a month, 3 days, it's been reduced by, well, a factor of 8. So you've got almost a 90% reduction in concentration in a month. Well, the question is, how far can the substrate migrate in a month? If you've got a groundwater velocity of, 10 meters a month or 120 meters a year, well then, you can migrate it 10 meters away. A lot of my sites, the groundwater velocities, I'm lucky to have 10 meters a year. So maybe you might get down a 1 meter downgraded migration. Well, 1 meter isn't very far. So then you're going to have to put really closely spaced points. With emulsified oils, again, distribution is absolutely critical. What we know about these emulsified oils is we can make little droplets. The droplets are smaller than the pores. They will migrate through the pores. What happens is, at least the emulsions we make have a negative surface charge. If they bump into a positively charged site on a soil particle, they'll stick. And they bump pretty frequently. So essentially what you have to do is you have to inject enough oil to fill up all those absorption sites on the soil. If you don't inject enough oil, basically the oil just sort of stays trapped right around your injection point. You don't get good distribution and you don't get good treatment. So you need to inject enough substrate and enough water to distribute the substrate. And again, we'll probably have a different webinar in a few months that'll actually talk about how to do those design calculations. Other thing to note is soils with more clay, more silt tend to have higher retention versus really sandy, coarse-grained soils have lower retention. Okay, different typical designs and applications, and I'll go through some of the different designs. Okay, this is a fairly typical soluble substrate system. Sometimes people do inject, but this is a sort of early design that lots of people used. They go in, They'd put an injection well. They'd inject a soluble substrate mixed with water. They'd flush it past the contaminants, the denapple pool, and they'd have an extraction well down gradient. They pump that water out. They might have to treat it in an air stripping tower. They add more substrate, and then they pump it around in a circle again. This is a really effective technology. It can work very, very well, but it does, well, it tends to be relatively expensive. You've got pumps, you've got pipes, you've got treatment systems. Tends to require a fair amount of operator control. If you're continuously injecting substrate into an injection well, the wells tend to clog up over time, so you got to get somebody out to clean it up. But you know, one of the big advantages is that you can spread it out. You can use somewhat fewer wells. Typically, I tend to see this kind of design is most useful where you have really high drilling costs or just simply access limitations. You can't get underneath a building or something. Another alternative that you see people using is they'll use essentially rows of biobarriers. The dark blue circles are supposed to represent one line of injection wells. And what they do is they put a line of wells in, they inject a soluble substrate, let that soluble substrate drift down gradient, and treat the aquifer. It's a cool idea, but at that last, you see there the calculations. If I put the injection well, the rows of injection wells, 1 to 3 months travel time apart, and I've got a groundwater velocity of 60 feet a year, or 5 feet per month, I'm going to have to put those wells 5 to 15 feet apart. At that point, they're not rows, they're grids, and you just have lots and lots of wells. Conversely, if your groundwater velocity is 600 feet a year, this may work very well. We tend to do a lot of emulsified oil barriers. Basically, the concept here is we would go down right in the source area, we'd put in a line of wells, we'd inject emulsified oil. As the contaminant flows through the barrier, it would be treated. Disadvantage, it doesn't completely eliminate the source, but it tends to be relatively less expensive. It can be very effective while you're doing something else to treat the source. Now, how can you do barriers? If you're doing solid substrates, here's a photograph of a trenching apparatus that I think I actually got from Bruce Henry at Parsons. That big machine will dig a trench. You can backfill it with mulch or ZBI. Tends to have very good performance, but you need a big piece of equipment. You can use injection points to make a barrier with solid substrates, but you have to put the points really closely spaced, and that tends to be fairly expensive. Or you can use emulsified oil substrate, EOS, and I've already told you about it. It's got little droplets, works real well, and I'll let Brad and Savannah tell you how wonderful it is. If you're doing a source area treatment, what we'll typically do is we'll basically just put a grid of wells and we'll saturate the whole area. That ends up providing really good treatment, can degrade the contaminant. Obviously, the material is mostly going to flow through the high K zones, but you'll completely surround and saturate the source area. Now, the key thing is if you have a big source area, this is fairly expensive. It's a lot of material. Another alternative is you can go into a source area or even a plume and put a sort of series of barriers. Now, the oil you're putting in might last, 2, 3, 4 years. And so typically what we would do is we try to space these barriers maybe 1 to 3 years apart. And then what happens is dirty water flows in the barrier, gets treated. Treated water flows out of the barrier and flows down to the next one. Presumably, if you put the wells 1 to 3 years apart, you've essentially flushed that entire area once every 1 to 3 years. And at the end of that period of time, you should have substantially degraded most of the contaminants. Advantages of this is it requires fewer wells, less substrate. Obviously, you're not going to get quite the performance that if you totally saturate it, but it can be a sort of good intermediate alternative. Bioaugmentation. Pretty much everything I've talked about so far is adding electron donor to the subsurface. The question is, do you need to add bacteria? As I said before, Bacteria that convert TCE to cis-DCE are very common. You typically don't need to add those. Bacteria that convert DCE to vinyl chloride to ethene tend to be less common. I don't want to say they're not present. They're certainly present at some sites, but there are also some sites they aren't present. But I think the other issue is even if they're present, they tend to grow fairly slowly. Now, if you've got time, you could wait and let the natural population grow up. But sometimes it can take 6 months or a year for them to grow up. And if you want to accelerate that, you might be able to add bacteria. In most cases, this is actually a relatively old slide. I guess typically what people do is they'll go out, they'll inject the substrate, they'll make the aquifer anaerobic, and then they'll come back maybe a month or 2 months later, and they'll add the bacteria. That requires a second mobilization. I know some people are trying to combine those together. It can work. It's a little bit trickier, but it certainly can work, and we're starting to do that more and more. The question is, should you bioaugment? Well, the bacteria are not cheap. They do cost money. The counter side of it is waiting is expensive. There's monitoring, there's permitting, there's all that other stuff. I think our bias that we've moved to recently is that we'll typically go out and sample ahead of time. If the bacteria are present at good numbers, we won't bioaugment. But if they're present, even at pretty low numbers, or they're absent completely, we'll almost routinely bioaugment. It just saves time, it saves money, and it in the end, you get a good product. It may increase your cost a little bit, but people don't like failure. And this is that sort of extra insurance that makes sure your project goes well. How do you know if the bacteria are already there? There's a number of companies out there that will actually do testing. The two companies, one of them Serum, which is a subsidiary of Geosyntec. The others, Microbial Insights, are probably the most common ones. You can collect a groundwater sample, you can send it to them, they'll test it, and they'll tell you whether the bacteria are there or not. Our experience is that if you go out and you sample before substrate addition, a lot of times you won't see any bacteria, even if there's small numbers present. The good news is if you do get positive results, you're pretty confident that bioaugmentation is not needed. And thank you.
All right, thank you, Dr. Borden. So now we will move on to the questions. So you can either send them through our webinar, GoToWebinar question area, or as you can see on the slide, you can email either me or Brad, and we will get in touch with Dr. Borden to get you the answer. So, okay, so yes, there will be a copy of the slides available in a few days with the recording on our website, as well as our YouTube channel.
Whoa, you have a YouTube channel?
Yeah, we do.
Wow.
Just go to www.youtube.com and you can search EOS Remediation, and a number of webinars and videos are on our YouTube. We got one. All right. If an aquifer is already highly anaerobic, is it necessary to add hydrogen donors?
Well, okay. Essentially, what you're asking is monitored natural attenuation versus enhanced remediation. If the aquifer is highly anaerobic and there are already lots of electron donors that are already there, well, then obviously you don't need to add them. But if it's highly anaerobic and there's lots of electron donors there, you probably don't have much of a plume. So it's essentially already going away all by itself. So I think the answer is if your plume is already naturally attenuating very effectively, then probably you don't need to enhance it. But if you have a plume, that suggests that something is missing, and probably our experience is what's missing is electron donor. Now, some cases it might be pH, it might be bugs, but typically if you've got a plume, you're probably going to need to do something to speed it up.
Okay, so the next question is, what prevents a barrier created with soluble substrate from moving down gradient with groundwater flow?
Nothing. That's why if you use soluble substrates, they, well, one of two things. They either float down gradient or they biodegrade. Our experience is, I think the data indicates that actually they don't float very far. The soluble substrates biodegrade so quickly that usually they're basically all consumed within, 10 or 20 meters, and you really don't get much downward migration. How do you handle low pH aquifers? That's a wonderful question. You attend the next webinar on how you handle low pH aquifers. But the simple answer is you add a buffer. And there's a number of buffers you can use. The key trick is that many aquifers are actually really, really strongly buffered. Sometimes they're strongly buffered at a low pH, and it really takes a lot of base or some other material to raise the pH up to the target zone. But bottom line, you add a base and call Brad, and he'll tell you more than you want to know about.
And there is a presentation, I believe, on both our YouTube channel and the website on treating a low pH aquifer. So that is a good question. So the next question is, how accurate are estimates of the life of a zero-valent iron wall?
Number one, I think you really need to talk. I would not claim to be an expert of ZVI walls. I think if you're talking about a ZVI wall where they actually trench the material in, typically what they do is they end up putting a lot of iron in those walls, so they really do last a long time before they're depleted. People that use like nano and micro iron typically are putting a whole lot less in, and so they tend not to last nearly as long. But I think there's good data on longevity of the granular iron walls, longevity of the nano and micro iron walls are, well, a whole lot scarcer.
Okay. Any more questions that we can finish this up with? Nope. All right. Well, thank you everyone for attending. As we mentioned earlier, this will be available on our website. So feel free to send either Brad or me any questions, and we appreciate your attention.
Thank you.